Hello, the robotics committee. We are the team A from the University of Stavanger, and we are going to give our final presentation for the final competence of the 2021 robotics virtual reg competition. The contents of the presentation are the following ones that we're going to be presenting in the following minutes. So the team members of the robotics team are the following one. Rishank.
Hi, I am Rishank. I am pursuing master's final year in computational engineering. Currently, I am working in robotics team on drill string dynamics.
Hi, I'm Melissa. I am doing my master thesis in petroleum engineering, and I'm in charge of the models optimization and integration.
Hi, my name is Fazlul Haq. I am master's first year student in computational engineering. I am developing the web GUI for our robotics team.
Hi, I'm Luis Saavedra. I'm the team leader of the UiS team A, and I'm doing a master thesis in petroleum engineering, and I was in charge of the development of the RTSA Simulator. Then we also have some other team members that helped to this project. That was Miguel Fernandez, that was in the first year of their master student. Then Samuel Ehsan, who was the master student in computational engineering, but he has to withdraw at the end of February. And then Renan Ruiz, who is master student in petroleum engineering, but he has some works to do and was able to be present here. So let's start with the simulation overview.
Yes, so I'll be talking about both our simulators, the well-designed simulator and the real-time drilling simulator. So for the well-designed simulator, we have developed a user-friendly and target drilling difficult wells simulator. So we have 7 different tabs. The first one is the well path panel, where the user is going to choose the dimension he wants, either 2D or 3D, and give us some parameters such as to vertical depth, north and east points, inclination, and azimuth. For the whole module, we have to provide the sections of the casings, the diameters, and the measured depths of each casing. For the drill string, we have inputs for the drill string itself, the type we are using, the OD and ID, the MD, the weight on bit, and thermal conductivity, and also the friction coefficient. For the fluid, we have to present the dynamic properties of each fluid we're using, such as the density, the flow rate, the mud temperature, and the specific heat. For the geotemperature, we have to present the information on the formation and the lithology of each layer inside the well. And the operation, the user will provide the weight on bit and the rate of penetration for the operation. And then the final is the results tab, where you can get 5 different calculated measures, such as the temperature profile, the pressure profile, the torque and drag profile, the bit uncertainty and bit errors, and the trajectory itself, where we're going to see the DLS and the ROP of the well. And under the slides, we have the well planning design simulator, which is the website where you can access this. So these are the models we are using for the well design. We have torque and drag, which is Adnol's model. The temperature model is et al, and it's based on the energy balance between the formation and the well bore. With the flow model is Hirsch-Buckley model. The cuttings transport is Larson's. The buckling model is Dawson and Parsley for the deviated section, and the Lubinsky's for the vertical section. The ROP model is Bingham's model right now, but we are updating it to contain other models such as Mutahari's. The bit error model is ISCWSA model, and the trajectory design is constructed by the Bezier curves model. These are the references for the well-designed simulator. So the real-time drilling simulator, we have the following models: the RSS model, the drill string dynamics model, the ROP optimization model, the dual-bit model, the BHA model, and the optimized and models analysis. So for the real-time journey simulator, we have the following flowchart where the ROP model would provide the value of penetration rate. The drill string model will calculate the values of weight on bit, and the BHA model will be in charge of the sliding factor and the steerability values. These parameters are going to be sent into our RTSA simulator, and the simulation will then be performed. So if we find that the values are valid and these models have been validated, they are then going to be sent to the GUI. And otherwise, the sensors should pick up some issues and provide the BHA, the ROP, and the drill string model with some new parameters. And these parameters would then modify the values, which will recalculate the simulation. And some new features will be added to the real-time drilling simulator in future projects.
Hi, I am Vishen. I am presenting about drill string dynamics. Finite element method is used for modeling and simulation of drill string vibrations. The drill string is divided into a number of elements, where the last element is BHA component. For modeling of drill string in finite element method, two-dimensional beam element with 8 degrees of freedom has been considered. Each node has 4 degrees of freedom, namely axial, lateral, torsional, and bending displacements. The drill string is made up of steel. Each element has model for stiffness matrix and mass matrix using displacement method and consistent mass method. The damping matrix is modeled with the linear combination of mass and stiffness matrix for local elements. The local elements of the system need to be transferred to global system. For this, transformation matrix is being modeled with from the global matrix, global stiffness matrix and mass matrix. Dynamic equation of motion is solved using Wilson theta method. Then we need to impose boundary conditions in this model. In this model, the top of the drill string is assumed to be constrained for axial, lateral, and bending displacements, and surface constant RPM has been applied. The weight on bit and torque on bit are applied at the last element of drill string. So the weight on bit is obtained from surface weight on bit, which is in combination of downhole friction factor and inclination. The torque on bit is modeled in combination with weight on bit and downhole friction factor. So torsional vibrations occurs due to frictional forces between drill string and BHA. These vibrations can cause damage to drill string component during the downhole operations. Understanding the cause and reducing torsional vibrations by implementing corrective actions helps in drilling optimization. This is main focus of our study. To evaluate the torsional vibration and stick slip severity, a mathematical formula has developed, which is named as stick slip severity. From the figure 1, we can observe the stick slip is greater than 1, where the system is in stick slip phase. In the second model, the system is having stick slip value is less than 0.5, and the system is stable in stable condition. So based on the stick slip severity, it has divided into 3 regions. If the value is less than 0.5, the system is said to be in stable condition, which can be observed from figure 1. From the figure 2, we can observe the system is getting into dynamic region, which is dynamically unstable condition. The stick slip value for this region is 0.5 to 1. If the value of stick slip severity is greater than 1, the system is said to be in stick slip motion. We need to understand the effect of surface weight on bit and RPM on the drilling downhole torsional vibrations. From the figure 1, we can see that if we have constant surface weight on bit and constant surface RPM, the system is entering into the stick slip motion. In second case, after certain drilling time, the surface RPM has been increased with the same constant weight on bit, and the system dynamic vibrations is getting dampened. In the third case, initially the surface RPM is higher, and later we have reduced the surface RPM, and we can observe the system dynamics is entering into stick slip phase. So from this we can understand the weight on bit and RPM are important parameters to understand the stick slip severity in torsional vibrations. So in this frag, we can see that we have simulated for various weight on bit and RPM combinations, and the green region is the region where the stick slip severity is in stable condition. That is, the value is less than 0.5. Whereas in the red region, we can observe the values are ranging from 0.5 to greater than 1, which is either the dilution vibrations are in a slip phase or in a dynamically unstable condition. So we need to understand this combination of weight on bit and RPM to ensure proper drilling practices. So we know that torsional vibrations occur due to friction component in bottom hole interactions. So in this simulation, a dynamic excitation is added to downhole torque, and we can observe with the deterministic case, the weight on bit is 3000 newtons and RPM is 15, and we have achieved the stick slip value of 0.158. Whereas in a random excitation, the stick slip value is ranging from 0.5 to 0.18, which suggests that even though the system is in stable condition, due to random excitation, there is uncertainty involved in stick slip procedure. So by running these simulations, we can we found out that increasing the rotary speed will decrease the stick slip severity, whereas increasing the weight on bit will increase stick slip severity. And we also noticed that the downhole friction conditions are in random in nature. In next diluting competition, we are going to integrate this diluting dynamics model to a complicated TD trajectory, and also integrate this model to RSS model, BHA model. This is not it.
Okay, so now I'm going to introduce the RTSA Simulator. So that RTSA Simulator is basically in two things. The trajectory control optimizer and the RSS model. The trajectory control optimizer gives the instruction to the RSS model, which simulates the bit behavior. And according to the bit position simulated, the trajectory control is going to determine if it has to change that instruction or has to keep the instruction according to the azimuth and inclination. The architecture of the RTSA simulator functions in the following way. It has the planned well path function, deviation control function, and a correction path function. These three belongs to the trajectory control optimizer and the RSS model that are these two functions. So basically the planned well path, it gives the trajectory to follow or the instruction to follow to the offset who interprets the forces and the deviation that the BHA has to have, and gives those information to the RSS model which is going to simulate the behavior of the bit. Then, according to the bit position, is going to be determined according with the deviation control that the bit is deviated or not. If it's not deviated, then the planned well path is going to give the next instruction to the RSS model. But if the bit is deviated, the correction path is going to create a temporary correction path for coming back to the planned well path again and continue with the process. The planned well path function has the following philosophy, that is creating a trajectory and the optimal trajectory based on the dogleg severity that has to be less than the maximum dogleg severity stated by the user at the beginning, and it has to get the shortest MD or measured depth. And it's based on the Bézier method curves. And for example, here the red dots are the initial survey points that was introduced for the user, and the green line is the optimized well path. In this case, for example, we see that they are not passing through the points because they are finding that the dogleg severity could be too much if we pass through this point, so it finds that it's better to have this trajectory now. Then the RSS model was developed by the University of Stavanger last year, and is based on this tool that was created by Canric Norway, and it's called the Orient Express RSS tool, who has a particular way to create the offset that is dislocating this disk and pushing this disk against the formation in order to push the bit in the opposite direction. So the model has this essential part that is divides the ROPs in three dimensions. We have the ROP axial, the ROP inclination, and the ROP azimuth, which are represented in these equations. These equations are based on the tail equation, that is this one, but for the inclination and for the azimuth and inclination case, the weight on bit is replaced by the force on the bit in the azimuth direction and the inclination direction. And these forces are conformed from the force due to the natural displacement and the force due to the offset itself. Both are sum and conforms the force in the azimuth, and the same for the inclination one. Then the real-time trajectory control is in charge of checking the deviation of the bit, and is based on the following conditions. The dogleg severity has to be less than the maximum dogleg severity for the correction path. It has to get the lowest tortuosity possible, and it has to do the shortest MD for the correction path. These also are based in bit error ellipsoids, which involves the drilling parameter uncertainties. For example, in this case, the blue line is the simulation, and the real-time trajectory control do check if the bit is too far from the optimized path, that is the green line. And in this case, it's not too far, so it keeps drilling with the same drilling parameters. But when the real-time trajectory control detects that, okay, the bit is too far from the planet trajectory path, then creates a correction path that we call to return to the planet trajectory path, or the green line again, in the following these conditions that we already said. The best thing to look for the results is just to check what happened when the trajectory control optimizer is on and what happened when the trajectory control optimizer is off. For example, when it's on, this is the target or the final coordinate to reach, and we can see that the simulated and the optimized well path are very close. But when the trajectory control optimizer is off, we can see that there is an offset or a deviation, and it can create some problems in the real world. And this is due to the fact because the corrections during the simulation, like for example here, that returns to the planet well path.
I'm going to introduce the web GUI and our software. Our web GUI is very simple and user-friendly. Actually, it has only 3 parts in our web GUI. That is the depth-based data view, and the second one is time-based data view, and the final one is 3D graphical RTSA simulation. In our web GUI, we have used total 13 parameters in our depth and the time-based data. As we can see here, the ROP axial, ROP inclination, ROP azimuth, TVD inclination, and all the others parameter which shown in this slide. And for the 3D graphical RTSA simulation, we have used the TVD in our z-axis, and the east and the north is in the x and y axis respectively. For our web GUI final outcomes, we can see in these 2 videos. In the first video, we can see the time variable is in the x-axis and the others variable is in the y-axis. And it follows for the all others variable, which we already shown in our previous slide. And the second video, we can see our final RTSA simulation, and we already mentioned that in our z-axis we have shown the TVD, and the x and y-axis we have shown the east and the north. For developing this graphical user interface, we have used several tools. For example, HTML5 and CSS3 for making this exclusive UI design. And we use JavaScript as a programming language for making this web GUI more interactive. We have used a third-party library that called HighChart for plotting all the graphs. We also used Bootstrap for making this web GUI more responsive. And last but not the least, we have used PHP and MySQL for converting the Excel data into the JSON format. We have some future plan for this web GUI. That means in this year, we only use the Python code outcomes. That means the Python data, which we got in Excel format, and then we converted it into the JSON. But in the next year, we have a plan to do everything in our web GUI backend. And we have also planned to do some more user interaction. That means user can change anything in our web GUI, and we can see all the outcomes in our web GUI. Last but not the least, we will do more interactive web GUI design, and also we will add some more features like drag and drop option in future.
Okay, so the discussion on future work for our simulator are the following. So the gravity and reactive torque has not been taken in account into the RTSA simulator. Then the planet trajectory also that was created by the RTSA simulator cannot be updated or changed after the simulation has started, which could be a good feature for the future. Then the simulation did not use the VHS model yet. Also, that can be a good apport for the future. And then the fluids dynamics could be an interesting study in the RTSA simulator and can create a more realistic results for the simulator. And also, a very important thing is that each model needs to be integrated and tested. And also the sensitivity and uncertainty analysis using the artificial intelligence or machine learning application could be added, which can be beneficial for the future work in the next competition. And finally, a new based GUI application can be developed for the future. So I hope that you like the presentation, and that's all for us. Thanks for listening, and see you in the final. Bye-bye.
Bye-bye.
Okay, Shashi, you want to go through the questions?
Yeah. Okay, so
The first question.
the first one.
For the first question, UCS is involved in stick slip equation. In stick slip equation, it will only consider the rotational velocity, maximum rotational velocity, and minimum surface velocity. It won't consider the UCS of the formation.
All right, so in the case that in the test model, if we give you interbedded for formation, the model will not account for it.
Sorry, I can't hear you.
Sorry, can you hear me now?
Yes.
All right, so in the model, obviously right now we can assume it's homogeneous. If we give you interbedded formation, like we let you drill through shale, then a thick layer of limestone, then shale, then another layer of limestone, you will not be able, your model will not be able to account for that.
I'm giving the friction factor for I'm assuming only friction factor in my model.
The friction factor has minimal impact. The more important thing is there will be a significant change in your ROP due to the hardness of the formation. Basically, the unconfined stress or the strength of the for formation, the compressive stress. So this is something, when you talk about stick slip, this is something you definitely need to consider if you want to replicate the real world.
Okay.
Yeah,
so,
just
yeah, I got it.
Okay, so the second question, how are you measuring the and calculating tortuosity? Basically, I'm using a simple one that is the Wizardmans equation that perhaps I can show my screen. That is this one. Tortuosity, it has to be with the dogleg severity for the survey stations that are simulated and the dogleg severity for the planet survey station, and I measure that. So it's kind of basic, but it makes it work. Okay. So the next one will be what will happen with the dogleg severity for the correction. So basically, the user has two dogleg severities to put. The one is the first one that is for the plan. And in the case that you need to correct the dogleg severity for the correction, it could be bigger than the planned one, but only because for the correction we need to correct as fast as possible. But of course, it has to be like some settings that are according to the user. So if the user believes that this BHA only works until, let's say, 10 degrees of dogleg severity every 30 meters, So he can put that, and we can plan the trajectory with a number of 7, for example. But that's more related with the.
Let me clarify my question a little bit more. Maybe I'm just being lazy here to type short, but so in the case of a well path, let's say, for example, your RSS output is 10 degrees per 100 feet, and you keep missing, and due to the vibration, once you integrated the deviation model, and you only get 5 degrees per 100 feet. So your plan to hit the geological target or driller's target downhole start to go from 10 degrees to 12 degrees to 15 degrees. It start getting away from your model. So that's the question I asked. On the extreme case where your feedback loop is not closing the gap, but actually the gap keep increasing, is there anything in your model that is built to kind of say, okay, guys, we got to stop. We cannot go on anymore. We have to pull out. We have to do something else. Is there something built into your model to account for that?
No, actually, no. The only thing that could stop doing or stop the simulation is when the number of survey points. For example, we create like a planet well path that has some survey points, let's say 70 survey points. So the simulation will reach those 70 survey points, and then it will stop. That's the only way that it can stop. But if it got deviated too much, sorry?
No, understand now. But this is something that if you have a feature in this model, it is really, really nice, because for now, right now in the real world, we need to calculate and estimate that every survey point, or we take just to understand how far we can go. So if your model do account for that, it's very beneficial to the user. Just saying.
Mm-hmm. Yeah, we have like the beginning of this, we can say. So right now it's considering that we can reach, but in the case that we cannot reach, it will try to correct, but perhaps it will not get until the target point, and it will stop when the number of survey points are equal in the simulation and the planning one. But yes, we can say that it's elementary parts right now. It's just the basics, but for low cases, it's working.
Okay, sounds good. Thank you.
Then the next one, the tortuosity reflecting to depth path dependent friction coefficient. No, because we have considered that Wizardmans equation that doesn't take the friction coefficient in this case, because it was just some very basic, some extra step that we want to do. Then what is the simulation step size? Are you changing control sets points between survey station? So the simulation step size is something that you can calibrate. Right now we are working with 60 seconds. Every 60 seconds there's a simulation, but you can calibrate like every 1 second, every 3 seconds, or every 120 seconds. And of course, that will affect the simulation at the end, the performance of the simulation. And then changing the control set between the survey station. And now, right now, we cannot change the control sets, because once we start the simulation, it will run all until it finishes the current simulation. So it's something that we have to work for the future, because we have that thing as a must do in the future project work, that you can change while it's simulated. You can change the direction of the simulation. Then how are you incorporating randomness and variability drilling to your model? Right now we are just focusing on 5 parameters that are the weight on bit, RPM, the sliding factor, then the formation aggressiveness, and the specific energy of the rock. So those parameters are supposed to come from another models, but right now we couldn't integrate too much in that part. So we are working with some given parameters, and we are randomizing those with picking like adding an error range. So we have like those values are the mean, and the error range is like we have a top and a bottom, and we use a uniform distribution of that. So every time that there's a survey point, the simulator will randomize these values and pick one of these values for each of the 5 parameters. Then, are you using the leaves of uncertainty as a drilling window tolerance for deviation plan? Yes, we are using the leaves of uncertainty for that, and we are calculating that using the ISCWSA error model. That has to be with some matrices.
Okay, next question. Does the size of elements like affect the solution time? Yes, if we increase the number of elements, then the solution will take a lot of time to get solved. So we find a sweet spot between a solution simulation time and the number of elements, and we are using those accordingly.
Okay. And then the next one, the example you showed for the RPM looks very irregular and sinusoidal.
The example you showed for RPM slip look very regular and sinusoidal. Can you will try more realistic slip with extended duration at 0 RPM? Or like in the results we need to show. With like I can't go to the question like robot stays.
I can. This is Shashi. I can probably clarify that. In real life, when you do stick slip, usually when it sticks, your RPM is 0 for a few seconds. It's not instantaneous, right? So I think the question was related to that. Are you planning to look at a stick slip scenario where RPM is 0 for maybe a second? It depends on the drilling conditions, and then the bit freeze, and then it shoots up to a higher RPM.
Yes. I have few results where the the RPM will be like 0 at a stick place for some time. I simulated those kind of scenarios.
I was wondering whether you thought your model would tolerate that kind of wild variation on the stick slip pattern.
Tolerate in the sense?
So would your model still work? Your drilling control model would still work despite the input of stick slip rotation RPM being very irregular?
Yeah, like this is like basic model we are trying to simulate. So if we have like enormous values of stick slip, still the model able to get the results of those.
Okay, so I guess we can pass the next one. Are you using the input parameters sent to you? Or are you feeding them into the models? Yes, actually, that was a big issue that we have right now because we were working with like coordinates at first, because in February we saw the question and answer put in the force of the web page. We thought that we were going to be given the north, TBD, and east coordinates, so we designed like that. Then when we received the sample of how it's going to be the inputs, I made some change in the RSS code. And yes, we are working with the TBD and the WAC rate. So basically, I'm using the TBD, the WAC rate, and then if it's positive, I'm assuming that it's going to the east. And if it's negative, I'm assuming that it's going to the west. So that's why we are working on a 2D case. But for sure, our main purpose of the RTSA simulator is with the 3D cases where it was better, we can say. Then have you finished the integration of the models you presented? No, actually, that's a thing that we have to do yet, because it was kind of complicated to relate some parts. And also with the new approaches that we receive from the sample, then it says, okay, we have a lot of work to do yet. Then how fast do your model runs on average? Do you have any comparison on the computational time and real time? We don't have like a comparison with computational time and real time, but the simulation that we are using right now is around 30 seconds. Depends on how many points, depends on the TBD, and depends on the step size especially. Because right now we are using 60 seconds as a step size, so that's like 30 seconds for doing the whole simulation, the whole well. But if we're using like a step size of 3 seconds, that could take like 3 to 4 minutes sometimes.
The size of stiffness matrix will depend upon number of elements. For one element, the size is 8 by 8 matrix.
Are you using the coefficients?
The friction factor is like dependent with the downhole velocity as well. So it is like with a function of tan h function is also included in that model. So it will consider the change in downhole velocity with the friction factor. Stick slip mitigation control. Like when there is stick slip in the like if you observe stick slip, what we are trying to do is we try to increase the RPM, and the stick slip is getting to mitigated. Like we have showed in the presentation. Like there we can we have changed it with several input weight and bit and RPM, and we plotted a graph, and with this we can mitigate like suitable values.
Then one question says that what are the principal parameters that your RTSA optimization model takes in as inputs? Basically, perhaps I can show this because it's in more order. RTSA model. Here, the inputs. So these are the inputs that are needed for the simulation. So we need a tolerance. This is like the set for the user. What is the maximum tolerance for considering like the difference between two survey points are making a curvature. So basically something related with programming. Then we need the survey points, the maximum range of tolerance for looking for the distance of the attractor from the start and distance from the attractor starting from the end of the Bezier curves. So that's something that makes the simulation to optimize the Bezier curves. So we need a range to look for the best two values. Then maximum dogleg severity, that is also this is set for the user. Then this is exactly for the model, the RTSA model. So we need the sample time or the step time. Then we need how much error do we need to put, do we want to put to the inputs, so the 5 ones that I told before. So it's like to randomize to create this range of error, we can say. Then this is related with the BHA itself, the
Luis, you're muted.
Yes, sorry. sorry. Okay, so what I was trying to say is I was telling this, the principal parameters of the RTSA optimization model. So we basically use these ones. This is the time step, the error noise, or the percentage of error that we want to add and have like a range, like a top and a bottom range of error that is added to the 5 parameters that I told before. Then the maximum offset that is related with the mechanism of the BHA for creating the deviation. So in this case, if we want the BHA to create like or use all the opening of the BHA, we set like max offset equal to 1. Then we can calibrate that. And then this is the offset of the BHA. That in this case we are working with 6 millimeters. That's the opening of the BHA, and the maximum degree for the tolerance of the of the offset activation. So when it's going to detect this, that the simulator is going to detect when is going to apply the offset or not, basically. There are another inputs, but these are the most relevant because there are like plenty of inputs. Then, okay. So the next one. What was the biggest challenge you faced when working on the drilling models?
For me, in drilling dynamics, the integration of like the stiffness matrix and mass matrix into like a numerical code is a tough task.
Then in my case, was integrating or optimizing the paths using the Bezier curves, then using the uncertainty ellipse, make everything work and have like a trajectory that doesn't need like a human intervention during the simulation. Yes, it took a lot of work.
Yes, for me, it's probably making sure that we knew the outputs and inputs of every single model that we're using and finding a way to integrate them so that if you change one of those parameters, all the others would change in combination with that. We still haven't been able to compile all of the models together. So yeah, that's the challenge.
I just use all the data from the Python. That's why all the challenges related to UiS code, everything.
Okay. Any technical or not technical challenge you'd like to share with the judges? Well, in my case, I have to learn the uncertainty analysis. That was kind of challenging for me. I have to remember a lot of matrices, how they work. So basically, I have to remember those things. But the uncertainty was my main challenge. I spent like 1 month or 2 months, or 1 month or 5 weeks working on that.
For me, I have a mechanical engineering background, so drilling is like a different field for me. So I need to start from basics to understand what is drilling, and from there I need to start with forming matrices, then converting into like finite element code, and then again formulating numerical code like different methods like central difference method and Wilson theta method, and then getting those results and applying like uncertainty analysis in that. So it's a tough task. I use like almost all of my background subjects in that.
For me, it's just Python.
Okay. Then what would you like to see done better for the next year of the robotics challenge? One thing that I would like to suggest is like the input data that we are supposed to work with perhaps should be sent at the beginning of the competence, because right now we were developing our simulator. I guess also for the other teams, they were developing the simulator based only on the question and answer on the web page from the robotics. But when the sample of how is going to be the input data arrived, then that was a big change. So perhaps for the next competition, that should be at the beginning of the competition, so the teams could start to developing based on that input. Anyone? Okay, so the next one. How do you calculate the measurements of downhole directional sensor? Do you consider that the sensor are usually placed some distance behind the bit? What happens to the azimuth measurement when you are drilling vertically? So basically, the sensor right now, we are assuming that the sensor are measuring well, but we have added some errors in the scale factor with the ISCWSA model. One particular thing from the VHA model in our case, not the VHA model, the RSS model, is that we use the VHA that comes from Rick, Norway. And if you remember in the presentation, when we present the tool, the offset is very close to the bit. So as a result, we are assuming that we don't have to project the bit position from the offset. So we are assuming that we are in the same, almost in the same position. That's why we are not assuming that the bit is like further and then further ahead, and we need to project the bit, the correct position. So we are saving that. Then, does your model account from signal propagation delay, or you consider virtual measurements obtained on the surface instantaneously? So basically, we are considering virtual measurements because we are not considering the propagation delay yet. That's one thing that we should do for the next year also. Do you calculate the side force on the bit? Does this side force on the bit affect the lateral RP? Yes. We calculate the side force on the bit. Actually, that's one interesting thing from the RTSA model that was developed in the University of Stavanger last year, that it divides the ROP in 3 dimensions. So one is the axial, then the other is the inclination, we can say, and the other is the azimuth. So for the inclination and the azimuth, there has to be a force. So we calculate the force for the inclination, we calculate force for the azimuth, and we convert those into the ROP using the tail model, kind of the tail model that was adapted, this equation. Then, how do you verify your model? Well, that's one step that we have to do, actually. We have to verify those, all the models. The last one, I guess, is this. Have you attempted to integrate your models with the data from Group B team? No, actually that would be interesting to do, but no, we haven't, because we have been working until May, beginning of June, so no, we didn't have time, and I guess them also didn't have enough time. So I think those are all the questions in the chat. I don't know if you have any more.
Thanks, UiS team. Any other questions from the judges?
Any suggestions from the judges?